Greetings. So I'm going to explain about the project. This project leverages real-time weather data to provide comprehensive and location-specific insights across renewable energy estimation, AQI, crop yield forecasting, disease prediction, etc. By allowing users to select a location on an interactive map, this system derives the site's latitude and longitude, which are then passed on to the weather API to gather essential meteorological information, including temperature, precipitation, humidity, wind speed, sunlight levels, etc. This weather data forms the foundation for multiple analysis. In renewable energy estimation, the data helps assess the potential for solar and wind energy generation by analyzing patterns in sunlight intensity and wind conditions. Based on this weather-driven forecast for AQI, real-time data on pollutants and weather condition enables predictive analysis of potential health risks, providing an early warnings for vulnerable populations in areas prone to poor AQI. In agriculture, the project uses temperature, rainfall, and sunlight metrics to forecast crop yields, offering valuable predictions that can guide farming practices, resource allocation, and crop selection. Additionally, the system forecasts the likelihood of pest infestations and crop diseases by correlating weather data with environmental conditions that favor specific pests or diseases, thus helping farmers to adapt proactive pest and disease management strategies. All weather and analytical data are stored in Hive database, allowing for efficient storage, retrieval, and trend analysis.
Let's start with the sequence of this application. First of all, the user comes to our website and provides the user location. This user location is first forwarded to our backend application, after which this location is further forwarded to OpenWeather API. Now, from OpenWeather API, from OpenWeather API, uh, we get all the basic weather data back to our backend. Now, this weather basic weather details is then forwarded to our models, which will do the prediction and return the values for air quality index, solar power, crop yield prediction, and convergent report prediction. Now, all these predicted values come back to our backend, are nicely formatted and returned to our UI. Now, our front end is written as next, and our back end is written in Fast API. I will say my I will do this.
Okay, so let's look at the code implementation for our project. Uh, okay, so now in our project, we see that we have a client written in Next.js. Here, this is sending a location request to the backend. If I'm to show the website. Okay, now let's look at the implementation of our project. This is the home page for our website written in Next.js. Now, once we click Get Started, if we are to start our backend server again, it's first connecting to Spark and or Spark and Hive clusters in Docker. And once it connects and the Spark session is initialized, the app is started. So now, if we reload the page, we'll get prop data for our location, which is this latitude and longitude coordinate, which is by default our college is latitude and longitude. Now we can input different latitudes and longitudes here to get different results. For example, if I am to change the value, you see it's updating in the background. Then if we set the location, it is refetched and we get new data. So here, if you see values have changed, we get the soil requirement, which is the nitrogen, phosphorus, and potassium, which is required in the soil. We get the estimated price, which you can sell here per kg. We get the pH level of the soil, which is recommended to grow this crop, and pests and diseases which may affect in this climate for the top three crops. Now, if we go to energy usage, we see the amount of solar energy and wind energy which can be produced per hour. So if you see solar generation, it's zero point 0.9 kilowatts per hour if you have a single panel. And wind generation, you'll see in this climate, we have zero point 0.7 kilowatts per hour. Now we can go to air quality, and the live air quality is fetched as 154 in this current time. Now let's look at how the backend actually works and the flow of the app. So we have every page which you saw previously is sending a request to this backend. Now for the crops part, we see it sending a request to the crops info part. This is getting the complete weather from weather API. If you see from the open weather API, we get some crop details, the current weather details like temperature, humidity, and also like cloud level and etc. Now from this, we don't have all the required details to pass into our model. So we do a bit of feature engineering here in this function. We take in the temperature, humidity, and rainfall, which we get from the API itself. And now, if we need extra features, we are adding them in each of our crops. For example, in this crops, we see that we are adding extra details over here in above. We're loading the model and we're predicting here. Now, if we see for solar prediction and wind prediction, similarly in the routes, we go to the routes. The in solar power and wind power, we are getting solar power input. We require all these fields, but we do not get all these fields from our model. So we get the similar details as the same from our open weather API, and we apply feature engineering here to calculate these results. Like for example, if I open this, uh, we say uh, we calculate our values in this file. My bad. We calculate the dew point which is required here. We calculate solar position like zenith and azimuth based on angles and latitude. We transform the weather data and we pass to models. Now this is an overview of the how the routes are working. To get into the models part, we have implemented a PySpark random forest regressor for the crop yield part, and for solar power and wind power, we are using random forest regressor. And for AQI, we are using an SVR, which is a support vector regressor. Now, seeing the AQI model, as you see here, we're loading in the data set, we're training, we're importing pre-processing techniques from scikit, and we apply our SVR algo and we train our model here. Similarly for the remaining files. Now, this is an implementation in a neural network, which is an option we have also worked with, but for the sake of working with Spark and our big data tools, we have done in PySpark. And to show that model here, this is our PySpark model for random forest regressor. We take in the latitude, longitude coordinates. We prepare data here, which is applying latitude and longitude to the existing data set since they are not present fields there. And we predict our crop price, pH, and the NPK as you had seen in the client already. Now, finally, to look at the solar power and wind power. Similarly, here both of them are random forest regressors. We load in the data set typically and load our models. We get an R square score of 0.82 in both models. Similarly, in our wind power.